All right, we're back. I don't know if it's going to continue showing Dead by Daylight or not, but I confirmed I
And
did.
it is
Did it properly this time.
still Dead by Daylight.
I don't understand. Okay. Well, if anyone knows how to stream with OBS and not select a game, that would be great.
And it lost my video.
Oh, that I can fix. Give me a second. There we go. All right,
Couple technical difficulties.
we're getting there. We're getting there. So,
There it is.
yeah.
So our objective today, yeah, is basically to determine whether or not the motor drivers that we selected will work. They're only good for 2 amp continuous draw. There's a good chance that the motors that are on this car draw more than 2 amps, and we need to figure out if that's going to be an issue or not. So we'll look into the motors, look into the motor drivers, and we might have to find a new motor driver to use to power the circuit or to isolate the circuits. And if we're good with those motor drivers, then we'll start designing the circuit itself. Um, So I suppose for now, I wouldn't suggest doing the circuit diagram yet if you want to go back
Car parts.
to the detailed engineering page. Yes. Determine if motor drivers will work. Or maybe it'd be worth going straight to me sharing my screen for now, just so I can
Yep.
show off the
Feel free. Take her away.
suite. So, what we're looking at here is you can see that the large currents can reach a 3 amp max, but only a continuous current of 2 amps. So we have to determine whether or not the continuous current of these motors is going to be higher than 2 amps, power to 25 watts. To avoid damage, please use an external 5-volt supply when using more than 12-volt driving voltage. That's okay. Interestingly enough, when we were looking through these comments earlier, we came across this one, which was overheats like none other. He says he's using a 360 watt power supply, sending out 12 volts with 28 gauge wire, which is irrelevant for his conversation. And he says basically he only gets 1 to 2 minutes and had to wait for 10 minutes for it to cool down. But if he's suggesting that he was using his 360 watt power supply to full power, that would mean that the power. So interesting thing is power equals current times voltage. So 360 watts equals 12 volts. Well, I times 12 volts. So current equals 3 amps. Now, so this guy is complaining that the device was running at 3 amps and it couldn't handle it for a long period of time when it clearly states that it's only good for 2 amps. So his complaint is, I was running this too hard. I was running this too hard and it got hot. Therefore, I didn't like it. So we want to make sure that we don't do that as well. So let's take a look at this guy.
A flaming car would be pretty cool, though, Lucas.
Flaming car would have been pretty
Come
cool.
on, especially unintentionally. Yeah, and Nacho
Yeah.
Kitty can deliver the booze. It'd be a great party.
So let's see. Three, two. So we're gonna try and find some information on these motors. Um, So Joe, I don't think you were here last session. So this is the car that we're trying to use. This car has the ability to drive in any direction, horizontally or vertically. It doesn't have to actually turn. It can just shift, like translate instead of turning. It's a it's a pretty effective way of transportation. So we think we can do some pretty cool stuff with this car. Um, but it does have 12-volt motors, which suggests they're reasonably powerful, or hopefully they're 12 volts so that we minimize the amount of current draw through our circuit. Um, let's find some information on these motors. Supply power, rated current, 1 amp. Perfect. So they're only 1 amp, so that means that our device can actually, the selected motor drivers can run this because they're good for 2 amps. We have 2 motors run off each of these motor drivers. So here are the motor drivers. So yeah, basically we need 2 of the motor drivers. Each motor driver runs 2 of the motors. Each motor is rated at 1 amp, so we should be able to handle it. We might need an external power supply for our Raspberry Pi, but that's that's not going to be a huge deal. I wish I mucked 6 mandarin oranges. You absolutely can. I'm sure these wheels would be very expensive for for an actual road vehicle. But according to Glavin, you can use they use these wheels on things like forklifts.
Oh yeah, there's a forklift video I'll pull up in a bit. It's really cool.
Cool. Very cool. So let's say, let's kind of throw in some information here. Driver. Get rid of this. That wasn't related to us. It was just a funny conversation piece. Motor driver is good for 2 amps.
All right.
Amp.
I have this video if you guys are ready to see.
Yeah, here, I'll give you back control.
The trackpad just died. There we go. Can you see? Yeah, you can see it. Okay, guys. So you can move essentially sideways, forward, diagonally, twist around. And it's all about tweaking the ratio of the spinning wheels. So it's going to give us a lot of freedom when we're building an RC car, what it can do. Yeah, it works based off those rollers. Yeah, the joystick, pick a direction. It's going to be interesting though for us. It doesn't need to be something that a human can compute. Like a joystick is pretty simple to operate. Want to make it non-autonomous, it could do a lot more crazy operations that a human might not be able to comprehend in real time. Anyways, it's going to be really cool.
That's a cooler video than the one I showed yesterday. That was great.
Nice job. Yeah, it's going to be a lot of fun.
Roll back.
Yeah, back to you.
Okay, share your screen.
So it's going to make parallel parking really easy. It just goes sideways. There's no... Thanks, Nova Dragon, for the follow. Awesome.
Okay, so let's try this. I might give you back control, Glavin, so that you can start, so that we can look at um, the Lucidchart document
Yeah, for
and
sure.
start actually block diagramming something out here.
Okay. All right. How do you
So
think we should break this down?
yeah, this is going to be an interesting one. So I want to first reference this. I want to see if I can put this here. I just want to use this as a reference, so I'm going to push it off to the side.
Okay, good idea. So that was from the data sheet we found for the particular motors that we were using. Or no, that was
Yeah,
from the
so
controller. Which data sheet was this?
yeah, this is for the this data sheet was from the motor driver documentation. Basically, all we're going to get out of this circuit diagram is how to connect the battery to the battery to the motor driver, as well as the motor driver's power supply to our Raspberry Pi. Except it actually doesn't quite do what I want, but that's okay. This will show us how to do the 12 volt. That's fine. So let's start with this, and let's call this oh, maybe I won't have enough control. Motor driver. Nice battery. Motor driver. Can we give like titles to this? Yes, we can. This isn't going to be the most detailed circuit diagram. We're using a free piece of software that's a little bit more intuitive, but a little less visually pleasing when it comes to electric circuit design. Usually you'd use something like AutoCAD, but it's a little bit more of a learning curve. And to be honest, at this point in time, I'd rather use AutoCAD if I had the design already laid out on paper instead of trying to learn it on the fly. So let's do, this will be power.
I think at 5 gens, our car might explode.
Put power plus there. No.
Are you trying to get another connection?
Yes. Maybe this won't be as good as I thought.
What's that?
Yeah, that's better. And we're going to call this our. So that goes into the motor driver.
So can you talk, Lucas, briefly about why you have power plus and negative, what those represent?
Yes. So basically, when we have our battery, a DC battery has two leads. It'll have a positive lead and a negative lead. The negative lead is your ground, and basically, when you make an electric circuit, it needs to form a loop, and that loop is with whatever the high voltage or the high potential is, or the power positive. Power positive needs to eventually find its way back to power negative. So the idea here, this would be the simplest of circuits, which would be battery, so the energy comes from the battery, goes through the motor, and then goes back to the battery to make that circle. Yeah, so this power negative, everything that goes into our circuit needs to be connected to power negative so that everything is connected to the same low potential. The idea there is that is the energy-less state of our circuit. It's kind of like when you think of potential, a good way to think of it is a waterfall. So the high potential would be the top of the waterfall, the low potential would be the bottom of the waterfall, and the water wants to go from the top to the bottom. But with that in mind, the water will only flow if there's water there, just like the electrons will only flow if there's wire there or if there's an energy source. So what we'll want, so now we have our battery connected to our motor driver, and then we want our motor driver connected to two motors. So the reason we need a motor driver and you can't go directly to the motor is basically when you have a DC motor, you produce what's called back EMF. It's an electromotive force that can be very hazardous. We did an experiment in school one time. It's basically you plug a motor into a power source and you watch it on an oscilloscope, and you can see that a 5-volt motor, when it's instantaneously disconnected from a circuit, it will actually produce a back electromotive force that can reach along the lines of 10 times the voltage, or even in some cases 100 times the voltage, which would mean 50 to 500 volts. When you consider those voltages, they're not necessarily dangerous to people because they're such low energy, but they are dangerous to electronics because they can break down the insulation between components and cause short circuits. It'd be the same as dunking something in water. It would create the same short circuit in just a hot point where electrons are free to flow in a part of the circuit where you quite literally don't want the electrons to flow. So we'll need motor driver. Oh, whoops. No. So I might actually just take this to a. Can I like grab a piece off this wire or something? Can I connect to this point somehow?
Probably. Where do you want to connect to?
One of the motors. So I basically want to do this. Oh, you're better at this than me. Well done. Pull it down a little bit though, just to make it look a little cleaner. So what we're doing here is creating a common bus. So I'm gonna actually take this one all the way. How are you doing these lines so well?
I don't know, man. Are you seeing the little the circles?
Yeah, but my lines just do whatever they want.
And you want it over here as well.
This is fine. Well, I was kind of hoping to grab it off the same point, so that it's natural. So let's do it like that. So I'll
Right, you edit it.
Making new shapes. This is weird. Okay, so what we've attempted to do here. Oh no.
Oh no!
Yeah, this is going to just be an episode of trying to figure out lucid charts at this point. Actually, this is we're going pretty quickly, so I'm glad we're not doing it in AutoCAD. This is actually going reasonably well. So what this circuit is currently representing, this would be power plus. Power plus.
I like your style, Average Joe.
Power plus. Then this is power minus. I don't want that whole line to come out. Oh no. Whatever. It's fine there. It's happy. It likes it there. So basically, I'll give you a little rundown on this circuit. The idea here is we have a battery with its positive power supply. The positive power supply goes into the motor driver. The motor driver then supplies two motors by using what's called a common bus, and that common bus basically has it basically brings power into a it's called an H bridge, and it's a circuit that allows you to control two motors separately from the same power supply. So there will be an internal switch here that'll open and close to give power or not give power to this motor and to this motor, and also give power to the negative side of it and the negative side of this motor to reverse the direction. So basically, we've connected all of the negatives to a common ground, and we've connected all the... no, we can't do this because this is a DC motor, so we can't use the common bus. I'll explain in a second, and that's my fault. And now I'm just going to destroy the drawing.
The whole thing?
Yeah, I'm going to delete this line. Goodbye. We're learning together. This channel is to show the headaches of engineering. Yeah, what if we want a legendary bus? We always want a legendary bus. This will be a legendary bus. Here, let's do it like this. So power minus. We want to be able to switch these. So we're going to take this here. And we're going to take a new one. Oh, my lantern. Good enough. I give up on what I was trying to do earlier, Glavin. Trying to keep everything in consistent places. I'll just explain away my problems.
We'll fix it in post.
Yeah, exactly. Turns out live diagrams are challenging to do. Okay, so I changed my logic here a little bit. If So what we're trying to do here is basically we bring in the positive power and the negative power from the battery to the motor driver. And then inside the motor driver we have what's called an H bridge, and the H bridge allows the H bridge allows you to switch between the positive output of the motor driver being the positive output from the battery and the negative being the negative. So if I in software or in switching made this negative supply connect here and this positive supply connect here, basically that will change the direction of the motor, and that's what the motor driver gives you the opportunity to do. It switches between positive flowing out of this side and positive flowing out of this side so that the motor can change directions, and it can also help control the speed of the motor, and all of those things are done with 5-volt connections to the motor driver. So inside the motor driver, if you give certain pins a logical 1 or a logical 0, it will change the direction of power flow to the motor. And now please ask questions if you have any questions. If you're interested in knowing more, ask questions, because it'll only help me understand this better, and it'll only help you understand this better. We're all learning together. What about you, Glavin? Do you have any questions?
This is great so far. So if we wanted to drive sideways, then I think actually we'd have the wheels turning against each other. The front one's going backwards, and the back one's going forward. I think that would actually get us to go kind of translated sideways. I think there's probably a couple of things I'm missing there. But you mentioned this bit shift. So we'd have these wheels we want to go forward, we give it 1. And the wheels we want to go backwards, we give it 0.
Sure. I don't know exactly how the logic will work in this. That's what these connections here are for, and those connections will be coming from our Raspberry Pi. But if you recall, when we were working with our with our car when we were shifting left and right. Um, if you remember, like pin 9 on the Arduino, if you had a 1 on that, then and you had the other one grounded, you would see that the car would turn left. And if you switched that logic, the high and low logic inside your software, you would see that it would change direction. So that's the same thing that's going to happen here. So basically, we have 4 inputs here. 2 of them are for one of the motors, and 2 of them are for the other motor. If, let's say, for example, blue is a 1 and green is a 0, then this motor will go forward. And then if white and orange are 1 and 0 respectively, then this motor will go forward. But if this ended up being a 0 and this ended up being a 1, then this one would go backwards. And same story for this motor with the other 2 connections. Now this diagram isn't actually a perfect representation of what we're building here, because this diagram is using a stepper motor, and stepper motors basically need 4 control inputs because they have forward, backward, forward directional, as in like some degree of rotation, and backward directional, some degree of rotation. So it needs I suppose it's actually probably a communication protocol instead of just straight bit banging ones and zeros. What I mean by bit banging is the idea of just saying this is a 1, therefore it's a 1. It would be the idea of sending bits over a span of, or bytes over a span of time, instead of just sending a 1. It would be sending a 11011 to send an actual signal. But it's a little bit more complicated. The real reason we wanted this diagram for reference is to figure out how to connect the 12-volt power supply. We're not using a stepper motor, not today. Why isn't it called byte banging? Well, because when you're using bytes, you're no longer bit banging. If you're just using bits, you are bit banging, I suppose.
You'd be banging too much if you're byte banging. You'd be banging 8 times more, and that gets tiring.
Yeah, nobody likes byte banging.
That's the plan, Joe, is to teach it to drive itself. Last session we talked about the different peripherals we'll be connecting it to, such as byte banging, different peripherals like cameras and things like this. So it will be able to sense the world, drive itself, and do all the operations completely independently. And we have a couple challenges, such as little obstacle courses and things like this, we'd like it to be able to complete.
I'm cleaning this up a little bit. Need to approach this a little bit differently.
No time.
Yeah, really though. Darn right.
Yeah, so we're thinking cameras. We were talking about ultrasonic at one point. I'm not sure if that's going to stay in. So ultrasonic sends out kind of like a pulse, receives that, you can estimate the distance. But I find they're not very accurate. We were using it for our last RC car. And if it ran up against a wall on an angle, so if it hit a wall perpendicular, everything's fine because it gets the response. It comes back to it. I'll go this way. It gets the response pretty nicely. But if it's on an angle, a slight angle, it hits it and it bounces away. So we actually doesn't get the response back. So we found in our obstacle courses, it would think there wasn't a wall when there was a wall because it was a slight angle or a sufficient angle, and then just keep driving into it. So just run right into walls full throttle, essentially. So that was a problem. So we're hoping this time to try different approaches, one of which is to actually have 2 cameras, and similar to our eyes, to be able to estimate distance, because the picture in both eyes are going to be slightly different. So using some kind of some machine learning and some other mathematical principles, you're able to actually see how far something is away with the two eyes. Same as what we do as humans, but it's harder with robots. We don't get it for free. So there's some libraries in OpenCV that allow us to do that with 2 cameras and do some pretty cool stuff. Side cameras would be a great idea as well. one thing we did with our last robot is actually put the ultrasonic, so again, the distance sensor, we put it on a servo, which allowed us to pick the angle the head was rotating. So similar to an owl, it could just rotate 360 all the way around, and we could say, all right, look over there. Is it clear? Is there anything off into the distance? And if there was something close over on the left side, but there's nothing on the right side, maybe we can navigate over there because there's more space. So we could do a similar approach where instead of buying a bunch of cameras, we could put two cameras facing the same direction and then rotate these like a head on a swivel. Don't know if you have the pictures of the last head that we built.
I have the car right beside me.
Oh, you do? Actually, yeah. If you want to show the car, it's super cute. Uh, yeah,
Oh.
flying drone was a project that Lucas has done before, so we might do a drone later. But I think car is a good place to start. Uh, there's a lot more problems we have to worry about if it's flying.
Yeah, Glavin says I've done it before as if I've been successful before.
Wait,
That's not true. I had a drone that was almost successful once upon a time. So, this was the car that we used the night that Glavin and I hung out and basically tried to do engineering until 5 in the morning. Looks like a mess, but it was a successful design. Um, if you see on the front of the car, you see that you have this ultrasonic sensor. So you have basically an output signal and then a receiver. So this will ping, and then this will calculate the time that it took to receive the sound signal, and then based on the speed of sound, it will determine the distance to the object at that given time. And it's fairly quick, like within
It was microseconds.
one hundredth of a second. So you can ping quite frequently. And basically, we had it sitting on a servo motor. So the servo motor allows you to move 180 degrees under control to the left and to the right, or 90 degrees to the left and to the right. So it would basically swerve back and forth during the drive to try and determine whether or not objects are on its left or right, based on where it's trying to navigate. Yeah, exactly. Glavin did the coding, so he might have had that function. Who knows? Who knows?
Nova Dragoon was just looking over my shoulder the whole time.
I might have had a couple of bamboo drinks, so
A
I don't know
couple.
exactly what was written.
Yeah, I think what was written needs to be rewritten. But one of the problems that I don't think you mentioned, Lucas, was the wheels. Did you talk about the front? Like
The front. Oh yeah. So one of the biggest reasons that we're moving on to a new car design is basically we decided that we don't have enough control with this car because the front wheels are operated by a DC motor, but the DC motor has a lot of play. So, for example, if you see this little amount of motion that I'm showing from left to right there, as far as the DC motor is aware, that's perfectly straight. So we didn't really have a lot of control over the direction of the car as far as driving in a straight pattern. What we did to overcome that was basically instead of trying to drive perfectly straight, we would actually just start swerving and then average to a straight direction. Which makes sense. It's a crude way to drive straight when the solution should be just keep the wheels straight. Um,
Yeah, yeah, it was
yeah.
pretty rough
Anyway.
experience. But this new car chassis and the motors that we have, they're going to be faster, each independent, so we're going to have a lot of power there. And I think you said there's going to be, but what did you call it? Not a stepper,
Um, so there's wheel encoders.
wheel encoder.
So there's a wheel encoder built into the actual motors in the vehicle that we're buying. Here, I'll share my screen and bring that up.
Joe missed out on seeing your wheel encoder from school.
Oh yeah, I'll give you the whole ride. Oh, there's. Okay, so basically, when you look at this motor, you see that on the back of the motor it looks like an electronic, it looks like a circuit board on the back with where all the wires are connected, and there's actually 6 wires coming into that. And there's 6 because it actually has 4 of those wires for a control input to whatever controller you're using. And what that circuit board on the back is for what's called wheel encoding. And wheel encoding is the idea of determining the amount of rotation over a period of time that your wheel went. So it's really good for trying to determine how far you've navigated through a course or something along those lines. You would use that in a traversing pattern called dead reckoning. The idea is just take a measuring tape, map out the track, drive for X distance, turn at X distance, and you will come as close as you can to traversing the track properly, depending on how good your measurements were and how good your wheel encoder is. So, with that in mind, once upon a time when I was younger and when I was living in PEI and working at the wind farm and had very few friends, I was playing around with my Arduino in our basement, and I decided to tear this RC car apart that I was showing you. I'm going to give you back control, Glavin, so you can see my picture. So, in the back of this wheel, in the back wheel here, there's a hole in the wheel, and that hole in the wheel is so that I could put a photoresistor or an LED inside of the wheel, and a photoresistor over top of the wheel. And every time the wheel would do a complete rotation, my photoresistor would sense the light from the LED, and I would register that as a 1 in software. And every time I received a 1, I would say, okay, that means the car has traveled X distance, and that distance is approximately 4 inches, or the circumference of the wheel. So I'd travel across my parents' basement just based on the distance that it's traveled as the wheel rotates, and determine when I need to turn the car and things along those lines. So that was a pretty successful endeavor. Very crude. I actually developed that wheel encoder before I knew what a wheel encoder was. I just knew I needed to figure out how far it went. But turns out there's a name for that device, and you can buy it very cheap. The best way to do a wheel encoder, well, I suppose we'll find out if the best way to do it is what they're providing on the back of this motor. But what we used in school is basically a disc that had 12 holes inside of the disc, and it had an infrared transmitter and receiver. And every time that the transmitter and receiver were blocked by a piece of plastic because it wasn't over a hole, that would be a 0. And then every time it wasn't blocked, it would be a 1. And if 12 of those 1s happened, that meant it went 1 full rotation. And what's nice about that is 2 things. It gives you a little bit of redundancy, because the worst case, you'll miss 1 of those holes and only miss, an 1/8 of an inch of travel, instead of missing a full circumference on the one missed opportunity. And the second thing is, infrared is better than an LED and a makeshift photoresistor. They don't really work very well when Lucas makes it himself. Anyway, that's that story.
So it's going to be a little bit smoother with this new car parts. Lucas has lived a hard life, so try to make it a little easier.
You know what? When you spend a lot of time trying to figure out small problems like that, it really gives you the opportunity to figure out a lot of small problems. For example, actually, one of Glavin's great solutions when he was over here. This is very simple when you look at it, but it was a challenging thing to come up with. So on the photo, we were trying to figure out how to actually mount the ultrasonic sensor to the servo, and the servo has this little plastic cap that basically snaps into the top of it. And this plastic cap, we didn't have a way to get it to be perpendicular to the ultrasonic sensor. So we put a piece of foam on, stripped off some wire, wired through the foam and wired through the holes on the ultrasonic sensor to mount it. And it actually ended up being quite successful. It held very well until it crashed into the wall a few times. But, I mean, easy repairs.
It held up.
It held
So
up.
Nacho Kitty, you were saying earlier, what if we had cameras on the side? That's the approach we were thinking, is putting the cameras on that piece to rotate the head around. So hopefully it's a little better this time.
Yeah, we actually, we're considering, when we buy the camera, we're considering buying a stepper motor instead of this servo motor. So this servo motor can only actually go 180 degrees. It can't go a full 360 degrees, while a stepper motor can continuously go 360 degrees at whatever pace we want it to do, and it can stop at any point in time. So that would give us full control. It would almost be like a LiDAR of sorts, but with a camera instead. We would just have to be sure that the wires from the camera to the Raspberry Pi don't get tangled. So we could only do 1 or 2 full rotations before we'd have to unrotate. And on that point, interestingly enough, that's the same thing that wind turbines have to do. I'm going to go on a little bit of a tangent here. So with a wind turbine, wind turbines up the entire tower of the turbine are hundreds of cables, and in those hundreds of cables don't have a method to disconnect as the turbine spins. So if the wind is going in this direction and it continuously goes in this direction and it spins around twice, then those cables have become tangled enough that it actually needs to stop spinning and just stop producing power and unwind itself over a span of about 15 minutes before it can actually start picking up power again. It's not all that common that the wind turbine will actually go around 2 full rotations, but it does happen, and it actually causes quite a bit of loss when you consider how much those turbines produce, and you lose 15 minutes of production in a high wind day. Anyway, that's just an interesting side topic. What a nice way to solve that is you can actually get, I don't know if any of you would know what a split ring is. You use split rings in things like motors, and it's basically, instead of using a physical connection like a cable, you use a brush. So the brush just stays in contact as it spins. So it's like a loose pressure-based contact while it's spinning. You can use split rings for lower voltages, but when turbines are transmitting power at 35,000 volts, you get some pretty serious arcing and it's a lot of energy going through those brushes. So you sort of avoid using split rings. Maybe newer technology actually uses split rings. I'm not really sure, but I know that the turbines that I worked with, they just had the cable connections, and they were pretty solid connections. Anyway, that's enough of that side topic. Why is it called a split ring? I would assume it's because you're splitting the power connection so that it's not an actual physical connection, but I'm not really sure. Let's look up a split ring and see if we can find out why. So here, I'm going to take control again. So I suppose I might have actually been talking. It follows the same concept, but looking at it now, what I was actually describing is the split ring that's used for a DC motor. But the split ring is because it's quite literally a split ring. But the idea with this split ring is You want this conductor to change from positive to negative in a DC motor over time. So it's quite literally just a split ring, and the changing from positive to negative over time with a magnet nearby will cause the motor to continuously be repelled, which is actually what produces motor rotation. Now we're on a double tangent. We're just gonna now we're gonna be talking about now we're just gonna be talking about DC motors.
Before you know it, we'll end up on hydraulics.
Yeah, we always do. Yeah.
All right, how do you think we could wrap up the high-level circuit diagram, Lucas?
Okay. So, yeah, I'll give you back control. You can bring up that. You can go back to that circuit diagram.
Okay.
So
one of the questions you had was, do we need 2 battery packs, I believe.
yeah, so what I've shown here is basically we have one motor driver with a positive supply and negative supply, and we have the second motor driver with a positive supply and a negative supply. And again, that's connected to all of the motors. So the problem is we also need to connect. Oh, I want this to be bigger.
The motor driver or the wires?
The motor driver.
How big do you like it?
Just longer. Not necessarily wider. Don't need to take up more space.
Little pencil motor driver.
Yeah. Let's get it out of the way and open up a little channel here. So now we'll need to get rid of this. And the reason we might need a second power supply is because each of these motor drivers are only good for 2 amps. Each of the motors will draw up to 1 amp, and the Raspberry Pi is good. It can draw up to 2.5 amps. Now, the question is, are we going to be using the Raspberry Pi in such a way that it's going to be using 2.5 amps? I'm not really sure, and I would like to suggest that we're not. Let's put that to that common node.
So if we have 2 motor drivers, each at 1 amps, now we have 2 amps total. And the question would be, if we add other peripherals like cameras, would they add up to be greater than 2.5?
Yeah, well, so the Raspberry Pi can take up to 2.5 can draw up to 2.5 amps, and we've already theoretically maxed out the power supply from the motor driver. The motor driver has the capability. So to give you a little rundown, this battery is actually an 11.1 volt battery. So it's an 11.1 volt battery, and that comes into it's an 11.1 volt battery with 2200 milliamp hour capacity, and that capacity can basically, I'm not sure what its max output is, but it's definitely above the amperage that we need. It's definitely above our limit of 3, 4 amps, 5 amps. There, good enough. But the problem is this motor driver has an output supply. So this would be a 5 volt. Oh no, 5 volt supply. So that 5 volt supply, and this would just be power negative. That 5 volt supply is generated by the motor driver. It basically has what's called a voltage regulator internal to it, and that voltage regulator can bring the 11.1 volts down to 5 volts as a secondary supply. But the entire output of the motor driver can only be a maximum of 3 amps for a short period of time, and then it can be a maximum of 2 amps continuously. So with that in mind, there's a good chance that if we are always pumping the motors as fast as they can go, which isn't likely, but if we are always pumping the motors as fast as they can go, then we might not have enough power to supply the Raspberry Pi from the motor driver without causing the motor driver to get extremely hot.
We just have to do whatever that guy in the comments did.
Yeah. Let's pump 3. Basically, what we're describing here is pumping 3 amps or more through the 2 amp motor driver, just like he did, and then we're gonna post a comment on Amazon saying we tried to draw too much power from this device and it got hot. This is your fault. All right.
What?
Why does it turn?
What did you do?
I'm just trying to give myself more space. So there's the 5 volt supply and the power supply. So basically what we've designed here is a very simple power supplying diagram. This doesn't have any of the digital logic included in it. So there's going to be logical pins that come from the Raspberry Pi into the motor driver that supply those 4 bits, and two negatives and 2 positives, to control basically whether or not this, or this are positive or negative, and that'll control the rotations of these motors. But I don't know if we want to show all of that on this one diagram. That might be a little bit too cluttered. Sorry, maybe that wasn't the best way to say that. Sorry, Canada. Okay.
I would like to have this thing drive for quite some time, so I would expect to max it out.
You would like to max it out?
I would like to max it out, and I think that would make everyone in this chat very happy.
All right.
And it can
All right. Well, with that in mind, let's get rid of this. Let's get rid of this.
Let's make it to last.
And let's say that this Pi is going to be connected from another power supply. This will be a 5 volt.
Did we do something similar with the last RC car? We actually had the motors off one power supply built into the chassis of the car, and then we had a separate one for the Raspberry Pi, or at least we're considering.
So one of the big problems that I think we were having with some of our misbehaviors of our car last time was the fact that everything was coming off the same 6 volt bus. So here, I'll bring that back up. So basically, these 2 leads are brought from the batteries that are below the car. There's 4 batteries down there. Each AA battery is a 1.5 volt battery, so this would be a 6 volt power supply. So we bring those into this bus, and this bus is a common bus. So if I connect this red to red and black to black, and I connect those to the Arduino as well as the motors through an H bridge, very similar to what we have here with the motor driver, just a little bit more crude motor driver. We had them all coming off the same power supply, which drains the batteries very quickly. The problem is, or my concern here is, we're buying new parts, and I'm a little bit more hesitant to fry them. Last time, I suppose it really comes down to the first time I ever try something, I usually just say, whatever, let's plug it in and see what happens. But now we're designing something from scratch, buying the proper parts, and I don't want to have to buy new parts, basically because we tried to willy-nilly power something from a certain supply. So what we can use for this 5-volt supply, we can probably get away with using 6 volts, have 4 AA batteries in series with each other, and then their voltages basically add when they're in series. And then we would have to take that power supply and splice the output connectors to the back of a micro USB that will connect to the Raspberry Pi. So here, I'll bring up the Raspberry Pi for a quick second. So in the Raspberry Pi, we're all oh, right, I'm not sharing my screen. I'm sure we will blow something up, Joe. Soon enough. Soon enough, something will blow up. Whether it's on purpose, I'm not sure. We haven't decided. um, but we're all very familiar with this micro USB input. So we need to basically make our own power supply for that micro USB. So what I'm going to do is strip back an old micro USB cable and connect it to a battery bank. So just the same thing that you'd see in a TV remote, except 4 batteries instead of 2. And I'll take the 2 leads and splice them into the micro USB connector, and then we'll just plug it into the Raspberry Pi, and that will be its power supply. And it'll be separate from the actual power supply for the motors. So with this in mind, maybe we could do something like these lines don't do what I want them to do. Let's just okay. So now what I'm drawing is basically the logical. I'm representing the logical pins. So we need
Should we make them different
4.
colors?
Oh, can we?
Probably. What
Yeah.
color would be indicative of what it means?
So everywhere that's power plus should be red. Everywhere that's power minus should be black. And then, yeah, power plus is red, power minus is black, and the digital cables can be any color other than red or black. But they should all be different. So we should have 4 different colored cables. There will be, here, just a sec, let me finish drawing.
Yeah. So while you're drawing that, so the power cables, that's just going to be for all the powering everything, but the digital cables are actually going to be used to tell it what to do. So forward, backwards, how strong it should be going forward. So providing the actual informative part, not just the
That's
power supply.
correct.
Yeah.
That is correct. That is the these are the program basically the wires that are gonna be respond to the program to the software. Have you put any consideration into what language you'd like to write with in the on the Raspberry Pi?
Uh, what's the rating on this channel? Is it PG or I think we should use brainfuck, and everyone should take a moment to Google that.
Is that actually a language?
Yes, it
I
is.
mean, I mean, if that's a language, I am in.
It's an esoteric language. Yeah, we could definitely use brainfuck. Not your kidding. I like you're brave enough to mess with the cables. Yeah, that's something that Lucas will do because I'm not going to feel confident too. I'm with you on this one, not your kitty.
Oh, yes, you will be.
Oh God, and
Yeah,
we're gonna be soldering too. I got all my soldering stuff over here. I'm
good.
all equipped. I even got a little holder that I got for like holding little pieces as you're soldering them, and I think I even have
Yeah,
I
you got
got
a sweet.
I got a whole soldering kit. Yeah.
Yeah, I was telling Glavin last time we chatted that my soldering kit was bought about 10 years ago, and I paid about $15 at the source. It was the cheapest kit I could find, and if I could have found a cheaper one, I would have. I promise.
Yeah, we'll see. We'll see. At least we have two of them. We could both go at it and solder some things. Average Joe has recommended Doge scripts, which I agree.
Is
Doge
that
script,
real?
yeah, Doge script is a real script, and you can compile it to JavaScript, which means we could. So if we have a Raspberry Pi, you can run Node.js on Raspberry Pi. You can have Doge script, which will compile to JavaScript, which is Node.js compatible. So we could 100% write this in Doge script, 100%. Totally do it. Do it for the memes. Then we
Do
then
it for.
we tweet Elon Musk and say, "Look what we built," and he funds us.
Speaking of, I want to start beginning these streams with uh, day two. For example, let's just say it now. Day two of waiting for Mark Rober and Elon Musk to stop in at our stream.
Stop in, yeah, just casual drive by.
Just come say hi. Shout out to Mark Rober and Elon Musk.
That's pretty sweet.
It would be sweet. That is the dream.
You just have to tweet at him every day for a year.
Yeah. Did anybody hear that story? There was a software developer that was building a game, and the game was basically might as well have been. I think it was called SpaceX. He basically just tweeted at Elon Musk every day. He said, "I'm going to tweet at you every day for a year until you respond." And he asked, can I use your like the SpaceX name and rocket names with no liability? And on day something along the lines of 165 of 365, Elon Musk tweeted back at him and said, "We probably won't sue you." No, no.
You can
Don't do
undo.
that.
Need to.
Okay, yeah, definitely. Oh, I did it again. No. Maybe I should have just did this in AutoCAD. But we wouldn't be anywhere near where we are.
All right, we have a new
Uh,
suggestion. We should write this in white space.
white space.
What's awesome though is you could actually write it. You could write it twice. You could write one in DogeScript, but in the white space of DogeScript, write another program in white space. Think about
The what?
it. It's totally legit. Yeah, not your kitty. I love it. That's gonna happen. So we got DogeScript, we got white space. Boom, done. Run it on an embedded device. Invest. Yeah.
So, Interestingly enough, our circuit diagram, our very high level circuit diagram, there's not a lot of information passed here, but actually I'm going to, just for consistency's sake, I'm going to say, actually, that's not true, up to 2 amp. From a simplistic perspective, this is actually the entire circuit diagram that we would need to run all 4 motors from the Raspberry Pi. Now, what we don't show here is that we need some sort of control input to the Raspberry Pi so that because we don't, since we don't have any sensory capabilities right now in this diagram, we would need some sort of control from the Raspberry Pi. So what we're actually planning on doing for our first step is to use the Raspberry Pi as a controller with no autonomosity, and basically we might go as simple as making an 8-way directional app on a phone and connecting to the Raspberry Pi over Wi-Fi and just controlling the motors from a phone controller, just to make sure that everything's working out of the gate. And then we'll start adding some sensory capabilities to get it to start looking at objects in the room, and adding the scripts required in whatever Doge language we think we're going to be using.
All right. So if we're going to build it a remote control first and not autonomous first, then I propose learning from Twitch, and we make it a kind of a crowd controlled version. We hook it up to Twitch, and people could send in commands over the chat like they did with that Pokemon and Twitch a while back. And we can stream the video that comes out, and actually everyone online can control it.
Yeah, I'd be into that. That'd be hilarious. That would be. Oh, did I lose? I think I lost. No, I still have your sound. Okay. I think that'd be a really interesting adventure. We would just make it so that they can't run into objects. So it would be from our perspective a randomly driving car that avoids objects, but from the user's perspective, it would be them trying to break our car by running it into objects, I'm sure.
Would you do that?
Let's ask the crowd.
Yeah. We could trust you, right?
How do we give the crowd user input?
Well, so the thing is, you could have it. What is it? Eight sections, because we can move diagonally. So they're just picking which of those different moves to make, and they could just vote. And I think that other game that went on Twitch for Pokemon, everyone voted in a period of 30 seconds, and we could change it to 10 or something like this, or so you had to vote rapidly. But yeah, so essentially everyone votes up, and then we say, all right, consensus is up, and then it would just move up 1 unit, and move around or rotate or spin or whatever it was.
Okay, and that makes sense. But would there be any opportunity for us to not have any say in what it does, or would we have to physically input it?
Wait, us? No, I was going to automate this.
Yeah, so I guess that's my question.
I was just going to put it at your place, because otherwise they're going to drive around my place, and that's terrifying. And then we would just put it on your place, turn all the lights on, turn the camera on, live stream to Twitch, and then it would just get in the text inputs and then do whatever it says on its own, and we just leave it, and anyone can just join and just drive this car around your apartment.
That would be fun.
Yeah.
That would be great. How are we getting the text inputs from Twitch, though?
Yeah, there must be a Twitch API or something we could use.
Must be.
And we could probably even run it on the device. I'd very much like to handle all of it on the Raspberry Pi.
I'm into it.
So you just essentially turn it on, it's connected to Wi-Fi, and just put it on the ground and then leave it. And it's just streaming. We can make it its own Twitch channel or something that people could poke at. I don't know what it has to do, but yeah. And then if anyone wants to say where's Lucas, they could just drive the RC car over to Lucas with horrendous lag. Ooh, it could be like a Mars simulation, because the lag is so high. It'd be like what it would feel like to go to Mars. micro USB is. We're not going to drive over him. Don't worry. Just drive to him, and then maybe if this robot has a claw in the front of it, we could drag him away. But that's version 2. What if he's unclothed? Do you get points? We could use object recognition. Every naked Lucas that you see. What rub? What does rub mean?
What is happening?
So we get points. So okay, here we have to have a point system, right? So you're driving around and you get different points based off like if you found Lucas or something like that. If you caught a picture of him, you have to like corner him in the room or something. Oh, yeah. The bra. Sure, it's bra. Rub. I think rub makes a lot more sense.
I'm wondering. I'm trying to. I hear Nacho Kitty losing her mind.
Oh, yeah, I agree, Joe. Yeah, that's what I understood as well, and it's also been okayed by Nacho Kitty. So
oh man,
I like this plan. So you're okay, right? We can just let this thing loose in your apartment for a week, maybe.
Is that a barrel input? Here, yes, I'm completely fine with that.
Perfect. I think Nacho's Kitty's a little worried.
Oh no! Oh no! It's powered by a USB micro power supply that can supply at least 2 amps at 5 volts for the Model 3B or 705 for the earlier lower powered. So we might actually have to go through the barrel plug.
The barrel plug. Is that
so it's powered by. It's powered. I think it's trying to say. I think this is trying to say that the USB on the micro USB on the newer Raspberry Pi is good for 2 amps, but the older ones weren't. So if you wanted to get more power out of more power to your sensors that are connected to the Raspberry Pi, you would have to, or before you would have to use the barrel jack, which is this guy right here.
Okay.
For your power input, but supposedly it sounds like this is actually now good for 2 amps. Yeah, there, perfect. Correct.
Okay.
So that means we can put. So everything I just freaked out about a little bit in my head was incorrect, which is great. The Raspberry Pi can take a full power input through the micro USB connection.
Okay.
Yes, and we need 2.5 amps. So if we want 2.5 amps, how are we going to get 2.5 amps? We could connect to if we connect it to a separate terminal block. So we might still need a voltage regulator. I want to use one power supply for the entire system. I don't like having separated power supplies. So what I'm kind of suggesting doing is, in comparison, if we're looking at this diagram, I would like it to come. So this is the power in to the motor controller circuit. And then one of these outputs can provide power. I think it's this one. Can provide power to whatever microcontroller you want because it has a voltage regulator inside of it that brings it down to the 5 volts that's required. But since we think that there's a good chance we'll be overpowering this guy, we want something else to be taking some of the load. So the power supply for the Raspberry Pi is going to come from an external source. And how we can do that is we could put a terminal block. So these are called terminal blocks where they connect, where they basically screw in. We could put another terminal block here. And then from that terminal block, we can connect to a voltage regulator somewhere over here. And we could also connect from that terminal block to these. So it'd kind of be like a splice point. Sure, Joe, if you want to take the load, you go right ahead. It's all yours. So let's see. I want to see large current can reach 3 amp max. Dual channel drive 2-phase or one 2-phase, one 4-phase, or 2 DC. To be honest, I don't want to get a voltage regulator.
Why is that?
Because I think it's going to be hard to find. Voltage regulator. All right, so I think I found one. Okay, so what does this guy do? Oh, not available anyway. My big concern with using one of these would be I don't want to connect to, so you'd have your input on one side and then it would come through the voltage regulator, which is this. This big metal plate is just a heat sink. So this is the actual device, and the capacitors are basically so that when the power comes, the power is shifting. A capacitor stores energy similar to a battery, and it'll actually keep your voltage at a stable level. Night, Canada. Have a good one.
Right. Thanks for joining.
But on the output, we would have to terminate 2 sets of cables in this, which my only real concern there, and it doesn't sound like something I would be concerned about, is that we would be connecting 2 wires, and we need to make sure that those wires are properly connected and not loose, or one of them is not like partially connected. Because this would be sort of a splice point. Unless, I'm just trying to think this through. I'm basically wondering whether or not we can splice a conductor somewhere else. I think we will get a voltage regulator, but I would like to try to not use it. We'll get one just so that we have everything at once, so that when we find out it doesn't work without it, we can find a way to use it. But we will aim to design the circuit as we have drawn here, which would be, well, this would be actually not as we drew here. I want to draw this a little bit different. 5 volt, so I need another block. Just trying to make a little bit of room.
Yep, that's good. diagram's looking pretty good. It's coming together.
Yeah, it's fancy, eh? Whether it's enough information, who knows?
Mhm.
I'm just kidding. It actually turned out a lot better than I expected it to. So we'll call this VREG.
It's a good recipe for success. Low expectations.
Honestly.
Ain't that right, Nacho Kitty?
Oh man. What are you saying about me? I know that was a jab. Okay, so let's bring that one to there. Let's bring that up there. Okay. Well, at the very least, we filled the page.
Nice.
Um, let's bring that up. Clean that up.
Oh my God.
Why would it ever think that's where I wanted to go with that Y?
I don't know.
Okay, there. So, what I'm doing here is I'm basically showing the circuit to connect from power to the voltage regulator and from ground to the voltage regulator to the 5-volt power, which would be the 5-volt power supply. So that actually converts it to 5 volts. That would power the Raspberry Pi, and that means it all comes from the same battery. What we actually should show is a terminal block somewhere, but it might be too challenging, so I don't know if it necessarily needs to be represented. Electrically, this diagram is correct, so all of the operating components are correct in this diagram, or at least theoretically correct. This is what I'm going to, or what we are going to try to design the initial car to. But yes, you absolutely should build a
That'd be a
robot.
great idea. Have you seen some of the robot battles before? They're intense. I was thinking about that too. We could get 2 of these. After we get one working, we could just order the same parts, rebuild a second one, and then do races. And
Yeah, that'd be cool. Or crash up derbies.
crash up derbies, little racetrack. Ring girl and the robot battles. Nice. I like it. This is coming together. Will we have enough pins left in the Raspberry Pi for other peripherals? Like we could put arms and things that will smash each other. That'd be great.
Yes, you certainly can be, Jawbreaker. That'd be phenomenal. So we would actually have to make this work properly, we need, or to make this diagram technically correct, we need to put a terminal here. I got to think about this for a second. So if that comes out, oh no, I would consider this technically correct. Actually, I would just suggest that this is a terminal block and this is a terminal block. That's fine. That works. So yeah, what we've shown. If anybody wants a recap of this monstrosity, as it goes, we need a power supply, a positive power supply to the motor driver. We need a negative power supply to the motor driver, and positive for the second motor driver, and a negative for the second motor driver. We need a positive power supply to the first motor, negative, positive, negative, and same down below. We have 4 control connections from the Raspberry Pi to control the motor driver. And these give you the opportunity to transmit 1s and 0s to these motors. So if this motor has a 1 here and a 0 here, it will go in the forward direction. If it has a 0 here and a 1 here, it will go in the negative direction, and that applies for all 4 motors. And these power inputs to the motor are switched within the motor driver based on the logical input that comes from the Raspberry Pi. So the Raspberry Pi is going to be sending a 5-volt pulse or a 0-volt pulse to the motor driver to basically switch between power positive and power negative to change the direction of the motor, which gives us full control, and everything can be behind the scenes after we build this circuit. So this is the high level design for the motor control circuit, and from here we could use something along the lines of an app or Twitch to control the autonomous car as people change the direction of the direction on an 8-directional pad of some sort, whether it just be an app that has. It could even be you could even use a joystick or electronic buttons or a radio connection, but nonetheless, we are going to. Yeah, exactly. That was Glavin's idea, to have the controls be posted on Twitch, and the video, basically have a video feed and the controls on Twitch, so that people could select the direction, and we would have the robot be looking for objects and avoiding objects in our apartment, but the users could, for example, be chaotic evil and try to run into objects, and our robot would have to try and counteract their controls by saying, no, I can't drive in that direction. And it would basically come to a null if somebody continued pushing forward and the robot kept saying no. I would assume that it would just stay in place, depending on how we code it, but we'll see what happens. That's the way I see it. Not
Twitch has to break the car.
We program the car to not break, and Twitch tries to break it. That's the way I see it.
I was going to call it Capture the Kamikaze, and then have it. The objective is to drive around, and they'd have to move it, and then there'd be one more command for take picture. And the idea would be to take a picture, like get into position where you are, then take a picture, and then that picture would give them points, or like go after chili or something.
I mean, that's a valid solution as well. Like you can give a Twitch user whatever objective you want, Glavin, but I think that people on the internet are continuously chaotic evil.
Yeah.
And will do whatever they can to be funny, and funny is usually destruction. So this is the circuit that we're going to buy the parts to complete. So we need to buy the motor drivers, we need to buy the connector cable, we need to buy the cable to connect the battery to the voltage regulator as well as to the motor drivers themselves, and we need to buy the car itself. So that's pretty much electrically everything until we get into adding more sensors to this diagram.
And this is the point of the call where we accept donations. So thank you very much in advance.
Thank you in advance. Also, you're welcome for a great stream.
Yeah.
Does anybody have any questions at this time? Anybody want to know anything else? Ask away, or make fun of our diagram, or. I take that as a no. Okay. Yeah.
What distance are we going to start acting on incoming objects?
It's a good question. With our last car, we were trying ranges. I think we were trying ranges around 1 foot before we would try to stop the car or have it react. That might end up taking some tinkering. I think that we should, in my opinion, Glavin can disagree. In my opinion, I think we should give it at least 30 centimeters so that it has time to officially react before it crashes into a wall. Because I'd hate to see the car crash into the wall and then decide, hey, I'm at the wall, and then stop.
Yeah, but this one's going to be so much cooler, right? because if we build it properly with the camera on the top, as long as it can rotate fully around, or at least one rotation, just have to do multiple rotations, um, then they could look in different directions as well. So they could crash into a wall, look behind them, and then just move diagonally or backwards, or it's gonna be a lot more flexibility.
You can take control back of the screen if you'd like.
I just want to show your face as big as possible.
Oh, great. Perfect.
What's going on?
Hello.
Did I steal your question? Gosh,
There's a lot happening in the chat.
there is a lot. Yeah, Nacho Kitty is having a rough time. Um, yeah. So I think it's going to be pretty nifty. Actually, along with those lines, direction we can move, I guess, 8 different choices. But I suppose we could also have them have 8 different choices of looking. So they could look one way and move another way. And I suppose that the voting doesn't have to be one action. We can move one way while looking another.
Interesting.
So
So if we're looking one way and moving the other, then the car would have no defense when running into objects.
oh yeah, it'd be great.
Oh, you want to induce chaos. All
Induce
right.
chaos.
I'm into it. That's fine. Um, what about you? Do you have any questions, Glavin? I kind of stole a little bit of the diagram. Does the diagram make sense? I know it's a lot of wires, but I think we followed along as we were going, so individually it's probably reasonable.
I think so.
Looking at it high level, obviously it's a little bit more challenging to determine what's happening.
I think it definitely needs more color. Like it's really important. This is aesthetically pleasing.
Aesthetically pleasing.
Yeah.
Oh,
So,
okay. Well,
uh,
that can be on you.
I weren't gonna say that, but okay. So, so these ones here, this should be red, and uh, so then those data pins. I'm trying to think of how we're coding this up. So the Raspberry Pi, we only have so many pins that the Raspberry Pi can use for motors, for cameras, for anything. Uh, how many does it have, and what do each of these things need? So we have 2 for each of the motors. It looks like right now.
RPi. Yeah, okay. So I'm just gonna Google that real quick. RPi pinout.
Yeah, we'll definitely need to add chili detection. I'm hoping that there's a certain someone I know with a computer vision and machine learning background that might be able to help us with that. But we'll have to heavily convince with some nachos as bribery food.
I don't know anybody that likes nachos.
Yeah, I know it's a hard bet, but nachos is all I have. Just piles of nacho chips and cheese and other fixins. So I'm hoping with these raw ingredients that we're able to find someone that happens to be a computer vision expert back in the day to help us build chili detection.
So it looks like we have 2, 3, 4, 17, 20. I don't understand why they lay the pinout like this. Here, you should, since you're sharing your screen, you should look up Raspberry Pi 3 Model A Plus pinout.
All right, let's do it.
Just let you have control for a little while. I'll take a little breather.
Is it Model 3B or 3A?
3A Plus, I think, is the one we looked at. Not necessarily sure why.
I just didn't think we needed one that had
More USB.
more HDMI.
Oh, right.
Unless you
Yeah.
want to take one of your spare monitors, put it on top. There's also a Pico. Okay, let's see. A plus is the latest and greatest, right? For
The 3 series. So A plus, I think the B came out first, and the A plus is the would have been the more recent model, but it's the more refined model, like you said, with just cheaper form fit kind of thing.
okay. My computer's a little slow. I think streaming is slowing it down.
I'm sure it does. What are you using for a computer right now?
Personal MacBook, one of them.
Is it the same as the one I'm using, the
Yeah,
2019?
probably even not as new as that.
Hmm.
Mine's if it would load,
Ah,
2017.
that is not the diagram we're looking for.
You want this?
I mean, we can use that, I'm sure, but it's a little bit more complicated.
Ooh, there you go. We got data sheets and such. Mechanical drawings, power, GPIO, peripheral addresses. Does the camera connect in a different way?
The camera connects. There's a display port output basically. It looks like it's like a 1, 2, 3, 4, 5, 6, 7, 8, like a 16 pin input. Probably connects kind of like with like a ribbon cable on the end of it.
Joe,
Oh yeah, if you mean it doesn't connect to the GPIO or it doesn't connect to the header
yeah,
pins.
yeah, that's correct.
Yeah, if that's what you're asking. Yeah.
Joe,
Okay, so let's
I'm
see what you
waiting for one
got.
of those new M1 Macs or an iMac, the iMac 5K. Those look beautiful as well.
So on here, it looks like there's uh, what's the highest number that you see after the letters GPIO? That's how many we have.
29.
29. 29 is probably the answer. That sounds right. So that's how many port pins we have to use. Sorry, I'm just
And
one
we
on my
need,
laptop.
for every motor, we need two, right? Strength
For every
and
mo Yeah, that's correct. And then for a lot of sensors, like an ultrasonic sensor uses 4, for example.
greedy. Okay, so let's make a list of this because that's going down pretty quickly.
Yeah.
So we got 29 GPIO. So it's a general purpose input output. And
Correct.
yeah. So we have 2 per motor. So that's, what is it? We have 4 motors, 8 in total. We have 4 per ultrasonic. 4 per ultrasonic. 4 per ultrasonic. Oh, I'm hearing myself now.
Yeah, that's my fault.
Oh, sorry, I forgive you. Camera. Camera is a different thing. So camera is separate. So we have the motors. We also have a servo, right? Because we're going to put it on a swivel head.
Yep, so a servo would need another 4.
Servo is a whole nother 4.
Yeah, so what we can do is, I'm pretty sure the servo, actually I can check right here. A servo is typically actually, yeah, so it's both, is the ultrasonic only 2 or 4? The ultrasonic is, both the ultrasonic and they're 2 GPIO pins and 2 like one there it's 2 GPIO pins, 1 ground and 1 power, and we can make a common bus for
Oh
the
yeah.
ground and power.
So then it's only 2. I'm just talking about
It's
GPIO.
only-
Yeah. Because we do common
Yeah.
buses for everything, right? Either,
We
uh,
can't do a common bus for GPIOs because um, if it needs to be a constant, basically, if we wanted to do a common bus for a GPIO, we would have to use what's called a MUX. It's basically a multiple input chip that allows you to switch between the inputs on the chip. Um, like basically, you would send a one. You'd use 3 pins to switch between 8 pins because you can make a binary 1 through 8 or 0 through 7 with 3 pins. So it basically transforms 3 pins into 8 pins um, by using timing. But I don't think we need to go that far. I've used them before. Yeah, that's what you used in that exactly. That
yeah.
that would be a MUX
So for
connector.
anyone else interested, yeah.
Yeah.
Yes, that's an option. But okay, so that's for the GPIO that we don't want to have to incorporate a MUX.
No.
Um,
But if we ever got to a point where we had, for example, several input like ultrasonic sensors, we can just time between them and use a mux. Like your mux is a lot bigger than what I would use. I would use a chip about uh, I don't know 3/4 of an maybe half an inch long and a quarter of an inch wide. Um, that has 16 pins on it. You've seen it. It looks like here. I'll try and show you. We have basically the same form factor chip on here. So see that little black square in the middle?
yeah.
Um, yeah. So that would be the exact same size as a mux that we would use for our um, increase of number of GPIO pins. And I might even have some still, just in my box of supplies.
Okay.
So those are problems that I don't think those need to be solved in our first order. First order is get the car to move around under some control. We have 29 inputs to play with, so we can buy a couple sensors, and that would be fine. The camera's off a different input, and that's going to be our main sensor. The servo or the stepper motor is going to take 2 inputs for when we get the camera.
How many
That'll be an
cameras
problem
can we
solved.
put on? Because I wanted to have two cameras, but that's a good point. If they're on a separate input, do we only have one of those inputs?
Yes. Darn.
Shoot.
Never thought about it.
That's upsetting. Synchronized dual cameras.
Hmm.
Yes, that's exactly what I want to do. We could just buy a binocular camera here. Take a look at this. Oh, it's so slow. Oh my God. Okay, here we go. Stereo binocular camera for Raspberry Pi. Uh, what else does it give us in terms of details? This is essentially what I wanted to build, but it's looking like it will just be a one piece that will do it. Oh my God, it won't load any of these images. So what's the connector called? Do you know?
On the Raspberry Pi, it's probably a Raspberry. Like if you wanted to Google it specifically, it'd be a Raspberry Pi um, display DSI.
Hmm. Yeah, Raspberry Pi expansion boards, but we don't have an expansion board. I worry this is not going to work for us too.
Yeah, it probably still needs the two camera inputs.
That's super upsetting. Yeah, that would make a lot of sense. Uh, well, I'm sad now.
That's okay.
Maybe I should go buy a Mac. That shoot me up.
A Mac?
Joe got me going.
Oh. 3 terminal voltage regulator, power supply 5. I probably have a voltage regulator here.
Just this little camera module. Just this little guy. How do I connect to?
Well, I think what we should do now is we should probably break away, call it a day for this stream, and get ready to buy those components, which would be the Raspberry Pi, the battery connectors, the voltage regulator, the motor drivers, the wiring, and the car itself, and then start playing around. So we have something.
Yeah, I think you're right. Worst case scenario is we have a car without eyes.
That's right. Out of the gate, I mean, if we build everything and we figure out how we want to lay out all the components while we're building it, because I'm sure we'll have more ideas as we're building it, we can buy the camera mid-build, and then it'll be here within the next, 2 weeks again.
Do you want to just get the basic camera, like the one camera? Because that's still better than nothing.
Yeah. We could even buy it right out of the gate. I want the camera, so we can buy that right out of the gate. We could buy that now.
Okay, let's do that.
Okay, so we'll get all the basics plus the camera, and that way before we even consider buying any other sensors, we can start working with OpenCV and trying to detect things in the room, and just base everything on camera information. We can put it on the servo for now, but I would have to put a lot more thought into which stepper motor to buy. I've never bought a stepper motor, so I don't really know how they work, and I don't know how to necessarily select the right one. So that might take another.
I think the servo worked out pretty well.
Yeah. I think it has potential. I think there's a lot of room for error on a servo, but at least it's a start.
Yeah, I like it.
Okay. All right, so let's call it a stream there and move on to the next one.
Awesome. All right, thanks everyone for joining. It's been a lot of fun, and we'll see you on the next one. It'll be great.
Good night, everybody.
Good night.
Hopefully next time we're ready to start building.